Hello, hello, hello. I am ready to tackle Advent of Code Day 10. Get my code here. It's running. Quokka is ready. I am ready. Here it goes a nothing. Okay. We have a grid. We have lines. We have two examples. Awesome. Let's take this one, shove it in here. Trim goes over there. We'll grab our second one while I'm here. This first, of course. Here we go. Since it's a grid, let me make it look good. Okay, what is this first one here? Trailheads, scores, blah, 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 blah. This trailhead has a score of 2. Oh, they're not actually giving me... That first example doesn't do anything. Great. Or it doesn't have an answer, rather. Does the second one have an answer? The second one was an answer of 36. Okay, time to start reading this. Height 0 to 9. Okay, so this is pathfinding. Uphill slope. Starts at 0. Ends at 9. Okay. Okay, so I'm supposed to do that. 9 trailheads. Okay, so there are 9 starting positions. Having a score of 5, 6, 5. Is there one exit or multiple exits? Multiple exits, so is this to your shortest? 2 trailheads. The trailhead at the top is a score of 1, while the trailhead at the bottom is a score of 2. Okay, I don't understand the scoring system. Why does this one have a score of 2? Oh, because you can reach 2 things. Right? This trailhead has a score of 4 because every 9 is reachable, except one immediately to the left. So 1, 2, 3, 4, except this one you said. Okay, so it's how many exits you could reach that determines the score of a beginning. Okay, I'm definitely seeing Dijkstra is going to get involved really quickly here. Let's start the parsing of this. So world equals data split new lines. Oh, let me turn Copilot off. Apologies. There we go. Map line. Convert that line back to an array. So I think we can build up the graph of things we can go to, which is going through all of these, finding my zeros, and then building it to, well, finding anything and going to all 4 siblings and building a graph, directed graph to go up higher. So const graph equals this for const, well, let r 0 r less than world.length r plus plus, let z 0 less than world. So we have row, we have column, and then we have world column. So const num equals world rc, and now we need to go through all of our neighbors. So for constant dir of, well, it's not direction, it is direction, but I will destructure it straight away to row and column offsets. So 0, -1 is left, -1, 0 is up, 1 is right, and 1, 0 is down. Then we have new rows and new columns equals ROC plus CO. We gotta make sure this is still in the world, so const neighbor equals world, and R, this could be off, so optional change, and C if neighbor not equal num plus 1. It could be undefined if neighbor fine. Continue. Then cost neighbor number equals plus a neighbor. Now I can do that check if neighbor equals num plus 1. Then congratulations, we can go from where I am to my new friend. So the graph would be, I guess first I have to do this one. Well, this could be optional, so let's do it in here. So cost num key equals to key, and then I'll just say RC key. Well, we don't need to turn those into keys. That should be enough. So if not num key in graph key is congratulations, you can go to a bunch of different places. I'm trying to think of how I want to break this. I think a normal Dijkstra would take it as a hash map, even though they're all going to be ones. Say graph and then key, then to my new place, which is 2 keys. I do need this one. Of C equals 1 because our weights are all 1. Let's record this out. String, what the heck? String to record of string number. There we go. Let's make that 2 key. Return nums join. There we go. Yeah, it can be anything. Well, it's an array of anything, not just anything. Function from key. Return nums dot, well, it's key. Key dot, freaking. I'm writing this because I don't know I'll need it. And their numbers, so map number. There we go. Okay, we got that working. Now we should have a graph at the end of this build. No? No graph? Okay, there's my graph. Where you are, where you can go, the weights to get there, we have all of that. We have enough for Dijkstra's. Just gonna go steal one real quick. Not whatever the heck that is. Just give me Dijkstra. You gonna do something for me, Google? That'd be nice. Yeah, okay, good. There we go. Now that will work. Boom, we got a Dijkstra. It's not typed. It's okay. Let's fix that. String record string number, but boop, starting node is a string. Okay, I'm not gonna type all of this. I recognize this from when I last grabbed it. I don't know if I want previous. I just want to really distances, but we'll suffice it for that. Okay, so we have this. Now we theoretically have Dijkstra. We need to take this and determine how many 9s each trailhead goes for. So it's finding all the trailheads and then finding all the destinations. So we need to keep track of those too. Well, really, starts, ends, is what they're really called. So hey, we do all this. Let's do it at some point. Well, after the number, right? So num equals 0. That's not as many equals as I wanted. Starts push RC. Num equals 9. Same thing for ends. That should give us those. Multiple starts, multiple ends. Boy, that's an awfully lot of them. Okay, good enough. Now, yeah, I think it's just going through for every start, see how many ends it hits. So for starts and just for sanity, I'll throw a break here. Distances equals Dijkstra with my graph starting at key start. And then we have distances, right? Look at all those distances. We got a lot of infinities in here. Okay, this didn't work. Yeah, what do you mean code from the internet that I just totally yoinked off? Why didn't you work? Ah. Okay, what's the graph looking like? Is my start not in the graph? That could be a thing. Oh yeah, that's not how that works. Start R, start C. Okay, how about now? Okay, good. Now we just need to go through every ending and count how many ends there are. So let's score equals 0 for cost end of ends. If distances to key and R and C not equal infinity, and score plus plus. And I just did the wrong symbols here, so let's fix that. There we go. That about right? Looks about right. Let's see what we got. We got a score of 7. Okay, so we have scores. You want to add me all the scores together? I can do that. All scores equal 0. I look forward to the inefficiencies that my solution has. 63, damn, a lot of scores. You're going to too many places, obviously. Okay, so they have scores of these. So let's look at the individual score. They all have a score of 7. So you make it to all of them. That makes okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Top has a score of 1. The bottom has a score of 2. Okay, I'm gonna take these and I'm gonna run on these examples. They said they weren't realistic because of the dots, but this is obviously gonna help a bit. Oh great, oh great. I hate. Why'd you do that when I pasted you? Okay, let me find the first example. This trail has a score of 2. Okay, let's do it. Score of 2. Let's figure you out. Let's. Okay, great. That was easy. Next one. This trail has a score of 4. Okay. 5. Aha! We found something went wrong. Not sure where. Let's focus on it. Move that up here. Kill that. So we got a score of 5, which means we meet all of our ends. Okay. 1, 2, 3. Oh, so you can't make it to this one. Yeah. So how do you make it to that one? Okay, so you basically say I make it to everywhere when in fact you don't make it to this one. So how does your distances say you make it there? So I mean it's in the first row, thankfully. Yeah, 0 row, column 2. 0 row, column 2. Row column. Hello? Distances. Oh, I mean, you make it to everything. Okay, maybe I'm reading this very wrongly. Well, I'm looking at this one, the one that's failing. Yep, yep. We have our graph. We start at 0, 3. 0, 1, 2, 3. 1, 2, 3, 4. Yeah, those are the 4 9s. Not supposed to touch this one, right? Except the one immediately to the left. Yeah, I'm counting 4. How many ends do I have? I have 5 of them. So you're saying I find all of them. Which ones do I find? 0, 2. No. If it's not equal to infinity. Of course it's not equal to infinity because it's undefined for whatever reason. Gross, 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 gross. If it's, what, not a number? Is infinity a number? I think infinity is a number. Nah, gross. Okay, I just need to check. Um, distance equals this if distance not equal undefined and distance not equal infinity. Gross. Will it work now? No, I have 0. What have I done? Not equal undefined and distance not equal infinity. So now I just don't make it to any of them. Has it been broken this whole time? Okay, everything's broken. Hello? These are the 2 places. These are row column, right? Row column, row column. If I goofed this up. 6066, 6066, and my distances are. What? What am I looking at here? What am I. You're not going to all of them? Is that what's up? Like, what about this previous thing? Are you doing some weird stuff here? Okay, no, that's just pathing. That's great. Why do you never go to the final thing? What do you mean, code from the internet? Why aren't you doing the thing I want? So they are here in the graph. The whole point is that you go through everything. While you have not visited everything, visit all the things. If there's nothing left for you to visit, no reachable nodes. Yeah. Okay, I guess I need to. Because my dice just not doing what I want it to do. Ah, great. So you're break. No, you're not breaking. When are you giving up? The while loop is killing you. Okay. All not visited. Let's see. You don't visit all of them. You're lying. Do not populate. Well, not visited and distances. So, okay, let's start here. We'll look at the distances. Yeah, all of them are infinity. Hey, you forgot one. Okay, wake up. Oh, because I'm only going through all the ones that can be gone to from somewhere else, not all the things that can be. I get it, I get it, I get it. I don't think I built this graph enough for the algorithm, which, I get it. Need to make an empty object for these, no matter if they never can go anywhere from there. So if not in graph equals this. There are no values here. It serves no purpose, but we need it for the math. Okay, great. So now that's working. I have a break in here. Let's get rid of that. Hey, look, it's working. Okay. Kill all of our logs because this is gonna work. I have a little expensive operations in there, but it's fine. No expenses up here. Okay, no expenses up here. Let's grab my input. Ooh, that's a small input. I wonder what part 2 is going to be, because that's going to have us doing something. 590, I'll take it. No, too big. Okay. This is always fun. I calculated too high of a score. Let me grab more examples. Well, I have to copy more examples, grab more examples. Drop this. Let's see. This contains 2 trailheads. show the top is a score of 1, the bottom is a score of 2, so it's 3. Okay, hey. Oh, it started working. Sure. Very fun. Here's a larger example. 9 trailheads. In reading order. 36. The sum of the scores of all trailheads on your topographic map. So, I mean, I know it's not the most efficient. I didn't expect it to not work. Um, Let me. This is just bothering me. I just have to fix this. If anything, this should actually be done up here. And this would allow it to actually always be there, no matter the neighbor bits. So this is more accurate now. Yeah, don't do the neighbor key bit. That's there, which means I don't need to do that. I can do it back in there. Hello? Okay, good. Did it change number? Yeah, I wouldn't have expected that to fix it. Okay. Well, what I can do is start visualizing it. Wouldn't be the most painful. It does fit on a screen, kinda. So I'd take a trailhead. I'd first visualize the path it can take. So I get rid of everything it can't take. And then I'd see the 9s it hits. That is the score, right? How many trailheads it can reach. Okay, assembling more fragments. Scores the number of 9 height positions reachable via a hiking trail. Yeah, okay. I believe I've made my graph correct, but visualizing it will be the great test. Let's turn you off and let's start with a old visualizer. Dropping all these because there's nothing cool to visualize there. Yes, we have all our scores, we have all our distances. Let's basically I need to make a copy of it here. Yeah, copy of the world here. So cost world. No, come on. And here we go. So for cost, well, I have to do everything for the whole shebang. Oop, oop, oop. Cost key equals to key, and then that is RC. There we go. If key, basically same logic as up here. Distance equals blah 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 blah. What is it? Distance is key. Then this expression here. More stuff. It means we made it. Else world RC equals a dot. Yeah, that should do the trick. We get rid of all the bad stuff. Copy world, not the main world. Boop, boop, boop. There we go. And then console log. Copy world. Is that small enough for me to see with my eyes? Okay, yeah, that's good enough. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 7, 8, 9, 5, 6, 7, 8, 9, 9, 9. I need to know your score after you do this. 5, 1, 2, 3, 4, 5. Yep, that makes sense. Okay, yeah, so this is good. I need to store, save, and then I'll put these in a nice way. Just yeah, this is nice. It's not enough. I guess I'll look at the next one. 1, 2, 3. I know this is not going to be debuggable on the main one, though. So, like, 0, 1, 2, 3, 4, 5. Thankfully, it's relatively easy to read on my own. Okay, I just need to make this a little easier. So, world copy, world map. Nope. Join space. Join new line. And score. How does that look? Absolutely horrible. Yeah, I don't think clock is going to be able to help me with this. Do I want this? I just want to do it one by one. I'll do it on myself. Console log the world. Console log the score. Yeah, that'll actually be my delimiter. Yep, so if I cd I think that will give me what I want to see. Yes, this is exactly what I want to see. Okay, so I see a map, I see a score, map, score, map, score, map, score. I can read and I can follow it. Okay, gonna run it on the real one then. Yeah, then a lot of maps. Okay, so score of 1, 0, 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8, 9. I kind of need to. What happened there? Oh, I'm already scared already because I know what's bitten me in the butt before. Dang it. Really gotta do something. Okay, it's working. I Me and Windows, we are not getting along. I don't know why. Okay, good enough though. We're running. It's running. We're running. What's part two? It's gotta be harder. A trailhead's rating is the number of distant hiking trails which began at that trail. Is it? Are we doing an inverse Dijkstra? Because that's what that sounded like to me. Considering the trailheads, they have ratings of this. Okay, it sounds like something about inverse Dijkstra. Second way to measure a trailhead, the number of distant hiking trails which began at that trailhead. For example, a single trailhead is rated 3 because there are 3 distinct hiking trails which began at that position. Oh, there are 3 different. Oh no. Okay, I'm not ready for that. Because Dykstra is just going to take the most efficient one. Okay. So it's 3 different paths. I do have previous, so I might be able to use that a bit. We have some good examples. Let's chuck it in. Let's get part 2 cooking. Just so I can get some output on this to see if I even have enough. Single trailhead with a rating of 3, aren't you? Okay. Let me turn off the X. We're not doing anything. Turn these back on just for good measure. And let's do this. Okay, of course, and I think we only have the one. We do. Okay, so we have distances. We also have this previous, which I just yanked it from. It didn't need it from me. Okay, it only has the one previous. If I store the multiple previouss, then it'll allow me to have the split here, the split here, and the split here. Distinct distinct hiking trails, rather. Okay, interesting. So let me just look at what we've generated. Dang, all that logging I had, I just got rid of. It's time traveling time. Here it is, and time travel back forward. Okay, we got it. Let's log it. Let's look at it with our terminal. Yeah, numbers don't equal numbers. Okay, so I can see them, which means they are in distances. How do I count them? Is it going backwards? How do I count these? Let me look at previous. All right, because we have, what are you? 0, 1, 2, 3, 4, 5, 6. So 7 and 6 are the ones I really gotta look for. Maybe it's 6 and 5. Okay, so 6, 2 is 5, 2. 5, 2 goes to 4, 2. So it's going up. 4, 2 probably goes to 3, 2. 3, 2 goes to 2, 2. 2, 2 goes to 1, 2. 1, 2 goes to 1, 3. So it starts going right. Okay, if I have that previous modified a bit to take an array of things, that would allow me to do what I want. Let's see if I can modify this really quickly. This is so gotta watch out for these nulls. Let's make you an array. Congratulations, you just got upgraded. And previous push. No, this should show me 3 of them with a double previous. Or not. I lied. I'm a liar. Okay, so 6, 2, 5, 2. So like 0, 1, 2, 3, 4, 5, 6. So 5, 2. You're the one who should be starting to do stuff. Get off of you. 5, 2. 5, 2. You go to 4, 2. 5, 3, 5, 4. 5, 4, 5, 5. 5, 5. 4, 5. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. 5, 5 goes to 4, 5. I think I just had that backwards. So 4, 5, 5 is 4, 5 before 4, 5. 3, 5. Oh, I'm on that. I'm on the column. Dang it. Yeah, my brain is hating this relational numbers. Yeah, I expected to get more out of that. I am not getting the more that I wanted. So we are traversing distinct hiking trails. Began to descend. I mean, I know a very bad way of doing it, but I'm not gonna anticipate it to like work with this because I have a lot. There's a lot of starts and stops, honestly. My God, did you do just go for the brute force? Because effectively, we do have the paths, its distances. So we can just refollow distances and be like, hey, you find a branch, branching universe. But it has to be a branching universe that can reach the thing. So it would have to follow to the end, not just see a branch, count a branch. Because there were a lot of branches that like ended up nowhere up here. Uh, okay, what if. So I have all the distances, I have all the previously. That's good. What if I go backwards? I go from the nines to the one. Wait, is it 1-to-1 scoring? Number of distinct hiking trails. You can look at the second example. Single trailhead for rating of 13. So single trailhead 0. 3, 4, 5, 6, 7, 8, 13. Re-hiking trails. Okay, well, okay, let me count this. 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah, you like count a lot. Actually, in that bottom left corner. Oof. I think I'm gonna have to go for the brute then, because I am not seeing it up on my head. I think it would be going backwards, because forward leads me like there's technically some dead ends there. So if I go backwards, I'll always eventually end up at the 0. Be dead ends there. Okay, I think maybe it doesn't matter. I mean, we have a nice world here. Let's ignore that. That was helpful for a bit. So we now need to, given all this, kind of calculate the rating. I look at the right one. No, I'm not. Get rid of you, get rid of you, and let's get rid of you while I'm at it. Okay, I really wanted previous to do its thing. Let me try and poke previous one more time. If total distance less than the distance to that, basically you find a new one. Yeah, this is the only time you ever set distances. Yeah, you're doing the find, you're visiting it, going through all neighbors, you're adding the previous's. Okay. I'm trying to think of the fancy here. The fact that it's here means we do eventually get there. So I think we just got to go back from it. What the heck? Did I break previous? Why is this broken? 0, 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3. Oh, 6, 3. Okay, that's what I'm looking for then. Or 6, 2 rather, and then that goes to 5, 2, then 5, 2 goes to 4, 2. Yeah, okay. So once I'm at 6, 2, I go to 5, 2, then once I'm at 5, 2, I have 2 places to go. Ah, there it is. I understand why the previous wasn't adding all the things, because I was only doing it for the distance. That should do it. It's going to be a lot of them, but I think this is what I wanted. Here are all my branches. Okay. Now, it's backwards, but that's perfectly fine, because I think that's what we wanted. So I go backwards, and then every time I find a split, boom, new possibility. Okay, we can do this. Function calculate. What am I calculating? Ratings. Okay, I need some information. Now let's be bad. Let's shove it in here. We have those. I will try to do this stack-based iteration, but Yeah, because recursion always can explode my face. So let's see. Paths equals here. Are actually trying to get to the start. So, well, it's from every end. So we need to find an end that actually has one and be like, hey, we found you. Calculate rating. So my end, and then is my start. Because now it is start end. It's going backwards. So path is here. Well, your one path is here to key from your start R, start C. Yeah, we have no types. Okay, we have all this here. And while these are here, we need to take one, pull the latest path, and traverse through previous's, all of them adding those back until get to the last previous, which is our end here. And there can only be one end, so that's gonna work. Yeah, I'm trying to think of optimizations, but I shouldn't be. I should just be getting it working. So false, which is paths dot length or false cross path up or const next previous to keys. Well, which is it? Current equals path at -1. Don't worry, you're not undefined. Current arc. Jeez. Current C. Ooh, these are the strings. I didn't put the things in here. Which would I like to store this in? Keys are things. The keys are in previous, so we're going to keep it in key land. So for const next to previous, and hey, that might not be a thing, so let's do this. If next equals, I'm going to calculate end key. Key equals to key and R end, not in code C. End C, so if next equals end key, congratulations, you just got one. Rating 0, rating plus plus. Else, then you're gonna go on the rest of them. Path stop push, my current path, and next. Now its previous is good. Okay, it's not typed, but that should suffice. That should be it. I need to put some brakes around here to prevent my computer from eating itself, so let's do that. Let's hit it up with a return, right? Oh, I'll have to look at the rating too with my eyes, probably. With the rating of 3. Oh, hey, that's a good rating. That's what we kind of wanted. Did I never closed up my loop. Oh, whoops. Hey, let's just go for it then. Computer didn't die. This might be the gold. Undefined. 3 equals 3. 1302. If this works, I'm really gonna be disappointed in myself. I should have just went for it. This is why you don't prematurely optimize, because you can think yourself out of a perfectly valid solution. Okay, we got it. Now let's figure out what they were asking for. So, back from the top. This is a fun one for sure. So what we have here is a two-dimensional map. This represents heights of places, I guess, from 0 to 9. Now, you can imagine a slope between these is like, oh, look, like this is a small slope between 0 and 1. But between like 0 and 9, no one can walk that slope. So the trick is that we're looking for a hiking trail that is even, gradual, and uphill. Well, I'm looking at this and my code doesn't do this exactly. My code. So you want a trail that is always with a slope of 1. Like you're always going up by a 1. You don't want to have any flat areas, you don't want to have any down areas, and you don't want to have any transitions where like you can't climb up it. Now, based on those, you have startings and you have endings. You start at the zeros, you end at the nines. So if you start hiking from this position, you can make it to 2 destinations. That is what determines your score. If you start from this 0, you can make it to 1, 2, 3, 4 destinations. You cannot make it to this 9 because there is no way, there's no slope available to get you there. The difference between 0 and 9 is not 1, so it's an invalid transition. Then they introduce that, hey, you can have multiple start positions, and those start positions can or cannot target the same end positions. In this case, I believe, yeah, so this bottom start can go to both this end and this end. So this has a score of 2. This top one can only go to this one because we go 4, 5, 6, 7. Then we have to go to an 8. The only 8 is down. But here we go 4, 5, 6. And then we have to go to a 7. There are 2 7s. So it can continue down both paths and get itself a score of 2. Big example, I'm not going to walk through it. For every trailhead or for every start position, calculate its score using that exact logic of how many ends can you reach, sum them all up, and that's your answer. Straightforward. I'd say not the craziest. Like as soon as I saw, I was able to, as you can see, figure out the idea. Just went and grabbed the old Dijkstra. Part 2 was the fun one where you need to count how many distinct paths or unique paths were there between a start and an end. And that determined not its score, but its rating, which is just the other number it wants to return now. Relatively good visualization of how that worked. It's, breaking through all the examples, giving them all how it works. Got a little stumped there going for the super optimized route. Eventually, I was able to just modify my Dijkstras that was already tracking previous positions to just track more. All previous positions, not more. And then traverse it backwards from the end, calculating basically every possible path and counting how many of those reach the beginning. Probably a better way, but it worked, so I'm not complaining. Yeah, that was it. Pretty good one, to be honest. I'm gonna clean this up a bit, commit it, and we will start on figuring out how this works. Okay, let's commit and stage. Do-do-do, do-do-do. 10. There is 10. Okay, so let's walk through this from the beginning. So, as always, we take our data, we get rid of them stupid character returns that Windows adds, and we turn it into an array of strings. I'm going to kill all but the real one as we walk through this. The real example, the real one. So we can see world turns into hello. There you go, turns into an array of strings, each one containing the cell value. Then we start to generate a graph, a directed graph from that has keys being the originating So like the from, values being records of distances to get to that from. It's more than is needed. I've written trimmed down versions of this before. I'm going to write it when I refactor it. But the end result is this graph here. Why is it really that computationally expensive? Okay. So it's saying if you're on row 0, column 0, and you want to get to row 0, column 1, it's going to cost you 1. It's like that's the weight of the edge between these two. We don't actually use weight at any point, so this is just to fit the data structure for the algorithm I copied, which is the common way that Dijkstra's is, because it loves it more efficient at the weights and all. But it's just here to say from here to here. That's the important part. And then if you're on row 0, column 1, well, there's nowhere for you to go. So that's like a dead end for you. So building this lovely graph is the first thing I need to do so I can feed it to Dijkstra. I do it by going through the entire world, grabbing the number, converting it to a key. I do this so I can store it in my hash maps, one lookup time, all that fun stuff. Make sure that every node is a key in the graph, because the Dijkstra I copied apparently needs that. I also keep track of all my start and end positions. So if it's a 0 or a 9, I'm like, oh hey, you're going in this list. I'm going to keep track of you for later. For every position we go to all its neighboring positions. I believe this one is left, up, right, down. We calculate our neighbor. If we accidentally walked off the board, so it's undefined, we ignore that. Otherwise, we're on the board. It has to be a number. We convert it to a number. This is a possible path we can go to of, hey, are they one higher than us? If they are, well, hey, let's say we can go from where we are to our neighbor with a weight of 1, which means nothing. So we have that. We have all of our start positions. We have all of our end positions. Boy, you're really not liking this one. Yeah, we have all of that tracked, and then we begin the process. Oh, let's drop this. That does nothing. Yeah, so I'll dive into the Dijkstra after, but we go from every start position. We're looking to calculate its score. Then we sum up all the scores together. So we call a Dijkstra on it. We say we're starting at the start position. That returns the distances it takes to get to every position on the board, which is information. It's not exactly what we're looking for. We care about how many ends we can get to. So as you can see, 0, 0, it could never get there. So it has infinity. That's our placeholder. We couldn't get there. And then all of these are the distances, or in our case, the number of moves it took to get there. So 0, 2, it took 0 moves to get there. I think that's where we started. Then all of these, you can see distances. The distance value matters not in our equation, because we don't care about that. But what does matter is, were you able to make it there? So like, is there a number as a value? So we get the distance, we check that it is a number, which isn't the best way of doing it, but for our data set, if it's not undefined and it's not infinity, then it is a number. We were able to make it to this end. Since we're counting up how many ends we're able to make it to, plus plus. We'll return it and we are done. Now the Dijkstra itself, I'm not going to explain the entire Dijkstra algorithm. There are many other people who explain it better, but this one I just grabbed here sets all of our distances to infinity. Our previous is a array of previous nodes to get somewhere. It starts off at 0 and it keeps going until it visits every single node. Then we have where we're currently at and where the shortest distance. Okay, yeah, this I don't recognize it a little bit because different than the ones I usually write. Which I'm gonna rewrite this in the refactor anyway. But yeah, Dijkstra's algorithm with the additional tracking of previous positions. That's what that does. Oh, I never used that function. Funny. Part two is everything's identical except for calculating the ratings, which required me to make that previous change in order to track. Okay, so I'm here. How did I get here? Which previous is? We look at that. There we go. You can see for the first example where it tells you where you came from. So and you can follow that to where it came from. And then the important part is that when you were able to get to this node from multiple nodes, it tracks all of them. So you're able to backtrack it and then split and be like, well, in universe A, I go this way. In universe B, I go this way. I sure hope they make it home, which by the definition, they should. And that is where our function here does. We have all of our universes, or all the paths we're trying out. We go through each of them. We're like, well, this is where we're currently at, going from the end to the start. Let's look at where the next ones are. If those next ones do get us to the end, which remember is the start, then we did it. We were able to find a distinct path or find a path. They're distinct because, well, we're not never going down the same path twice. Otherwise, let's try this other place to go. Yeah, honestly, going to be a nice refactor because it's going to return scores and ratings, and then it's just going to be up to the individual solve of which one is used. So I'm looking forward to this one. So I'll leave the Dijkstra part for last. That's not exciting. We'll drop from key. We never actually use that. So as always, let's do the parsing. So parse trails. What are we calling this? Give me the story. Lava. Can't spell the word lava. Okay, that's good enough. Let's do that. And let's just shove all the parsing logic in there. So this world graph starts and ends in my book. We have the world, we have the graph, we have the start, and we have the ends. Honestly, I think we're just going to want to return all of them. Starts and ends. Yeah. And let's just destructure that all up here. Const. And again, yeah, we will find the best layer of abstraction as we get into it. Okay, yeah, for every start, then we start calculating this. Just get close to the Dijkstra rewrite, but we're not there yet. I think for both, I'm just gonna do both, honestly. Ooh, or I could pass it a function that allows it to calculate scores independently. Or customizably, not independently. Okay, let me see. Measure trailhead. Yeah, I like that. So let's break that to solve trailhead measurement or measure trailhead. Let's call this a function that takes a start number, seed number. What other information do we need it to take? It needs distances or it needs previouses. And it needs ends. It needs a lot of stuff. ends, which is our number, C, number, it's an array of them. And then, well, do we actually need the distances? So we do use Dijkstra every time, but I'm not gonna go that level yet. Let's leave it here and let's just say, hey, give number. Then at this point, we can just say return start map, start, yeah, measure trailhead, start, end. Don't we need this? We just reduce. Sum, start. Oh, I'm messing all these symbols up. Sum plus measure start at 0. There we go. And now we take this function. And if we return solve data, like some of these parameters. Boop. Hey, there we go. And now we should return score. That access the graph. Okay, I need the graph apparently. No, I wouldn't need the graph if I did the thing. Let me look at part 2. Do I need the graph in here? No, I just need the Dijkstra. Yeah. So I'm just gonna say we're just gonna include that also here. So start and Dijkstra result, which isn't where you put it. I put it up here. Dijkstra result, which I'm gonna be cheeky. Return type of Dijkstra. Yeah, lazy. Oh, too many. Oh, no. Pushed all the wrong buttons. Got F, whatever key does that. Okay, great. So we have that. We have to pass it the result of passing our Dijkstra. So at this point, like, I don't know why I'm passing the starts, but we'll find out. Okay, so we have that. Let's get solve 1 in here. And here, boom, since we have types, we can just do that. Are my types not typing? Yeah, TypeScript isn't here, but it works, right? That it does. Okay. Since we're not explain mode, I can put those back. And this. I know it's a little computational. It's not. There we go. Okay. Turn that back off. So this works. I like this. I like this enough to say goodbye to that. And we're going to do the same thing to our solve 2 down there. And I should be able to yoink all of this. Just change that last to a return. Just destructure our previous. Boom, we got it. It's looking good. I'm liking it. Okay, so now we have a little bit of grossness narrowed down to just the thing that runs for every bit here. I think it's time to refactor the Dijkstra. Let me go for this one though. This seems like an easy win. For end of ends. Okay, hold on. I do 2 different data types for the same information. Do I need to keep these as objects, or can I go straight to their key variants? Because I just used their key variants here. I use their key variants in the actual Dijkstra call. Do I use their actuals? I just straight to a key and then end, which is start, goes straight to a key, and this goes straight to a key. So I don't think I need these to be objects. I can just cut out that middle data and just go straight to the keys. So to key, which I have num key right here. Let's just go for it. Bam, bam. Let's get these a little better types too. Boop, 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 boop. That breaks a lot of code below, but we got this. There we go. Yeah, it's cold. This code is old anyway. Let's get rid of that. Distances, yeah, no more two keys. We can just boop, put that right in there. I said boop and it didn't work. How dare you? Ah, this part also needs a boop. Okay, get in there. Let me just hit all the instances. I can drop this for start. Drop end key for end. Another one. Did I get them all? Hey, all the numbers are being spat out. There we go. So, unnecessary data transformations. Be gone. And better typing. Okay, I'm liking that. Let's drop the world, and if we don't need the world, let's not return the world. Okay, now we're getting to the point where all that's left is the Dijkstra rewrite. It's Dijkstra rewriting time. Okay, let's do this. So this won't be the first time I've done this, but got a lot of stuff here. So it's Dijkstra, but we don't need all the Dijkstra here, honestly. First we're just going to go with documenting with it currently is record string number visited, which is record string boolean. So it's really just a set. Don't know why we're using this data structure. Record of string to what is it? String array. There we go. Okay, so we have this. So we have all this initialization, grad level initialization. Visited. Why can't this just be a set? I want to make this a set. I'm making this a set. I mean, it's a set of strings to make you happy. If not visited, node. Yes, I hadn't realized this has no functional impact. It's all O1 under the hood, but it's used a better data set. Data structure, rather. Okay, yep, that works. All of the things are green, so happy to hear it. Next one. Yeah, there's a little bit of polish to be done here. I want to reduce just the data we're doing. Instead of doing this infinity, I want to not do this infinity. And I might want to reduce this to variable. I'm also going to want to eliminate the distance logic at all. Like the actual Dijkstra bit of it. I know, but we're not using it for this problem, so we don't need it. So let's just say, so once we get rid of this, we're gonna have to update some comparisons. So if you haven't visited it and the distance is less than the shorter distance, so here's the thing: when this goes, oh, be cool. I expected chaos. Yeah, there it is, because comparisons explode. Is it just here, or do I have to do it somewhere else? And now I have to swap infinity back in to preserve the behavior. I don't know if it also needs to be here. It doesn't like it. If less than distances neighbor. I don't have it up on these distances either, so I got a sneaky suspicion. Nope, that was it. Okay, just needed to make sure those didn't explode. And instead of doing the OR check, I'm just going to make sure it's in there. So if you haven't visited it, and there is a node in distances, and that distance is less than the shortest one, such just reads better to me. So if total distance is less than distance neighbor, which is another way of saying if you haven't visited the distance or your distance is smaller than that distance, go for it. Which I think I'm gonna wipe out in a moment. Yeah, we don't do distances. We just do +1, really. Total distance, which, yeah, again, we don't do distances in this particular usage. So we do need to put a value in here for the algorithm to work. So I think we can just say distances neighbor equals 1. Or we can put total distance so we have the incremental. We actually have a distance. I don't want to remove the data just because we don't use it. That's all we need. I'm liking it. I'm liking it. Try to see if we need the distances or can we just go for unvisited effectively. I'm going to keep the distances. I'm going to trim this probably. We have current node and current distance, which is just the distance of the node. So I can just get that from distances node. So if you haven't visited and you are looking at a thing you want to visit and it's less than distances node or infinity, yeah, this is where I'm fine doing the conditional. So now we have less variables to look at. I love looking at less variables. Still work? No. Current node, not arbitrary node. There we go. Yes, you can be null. Okay, I love it. Yeah, I'm gonna ignore that type. We can do empty string here. Okay, I'm liking it so far. Let's move some things around. Ooh. Okay, we like it. Like that. Like that. Okay, this is really just a glorified find, so let me rewrite it accordingly. Const node equals node in graph, so it's a keys find. Well, it's technically also a reduce because we're comparing to ourselves. It's good enough. I'm gonna leave that. Change that. Otherwise, boom, you visited it, you go through all your neighbors. We say we go to your neighbor, you add your distance to your neighbor. Okay, I like that. Might come for a little bit refactor later. But now what we can do is we can drop this from a record of records to a record of just straight strings. Well, not strings, because it still needs to support multiple arrays. There we go. And now we can drop that to an of and change our graph generation to support that, since we no longer just need to support them weird weights. Not weird weights, just unused weights. Okay, I think we have a few things that need to update to use the party, or no, that was it, yeah. Works like a charm still. Loving it. That's expensive. Yeah, I'm not gonna pick about it. Distances previous. Yeah, that's fine. I know what this is. Okay, I think I'm nearing the end here. I'm liking what I have. So of that part two, I want to make a little cleaner and this a little cleaner too. So instead of having to do this undefined or not infinity, since we don't have infinities anymore, let me actually show what distances looks like now that we got rid of all the trash. Boy, Wallaby's just struggling today. Quokka, rather. So now it's just an array of, or a mapping of, hey, here's this thing, here's how long it took you to get here. And we have no infinities. And I think even this is a bit much, but that would be post processing on the Dextra if you want to get rid of it. But now we can just be like, hey, let's just check if end is in distances. That's it. That's all you need to check for. Which really, if we want to go for super fancy, return ends filter. I mean, I'm not going to do it as a filter. I'm going to infer this even further. End in this distances the length. Ta-da! And to go even crazier, we throw a reduce on that. So score end score plus this to a this boolean to a number. Start off with a 0. Drop the length. That's getting a little weird to read, honestly. So I'm trying to think. Filter or because the third variant would just be moving this to a map. And then counting up the trues. Map. Reduce. What do you, is reachable? Lots of different flavors. What can I? Oh, maybe we can go super one-liner though. Ooh, the potential of super one-liner though. So let's see. This is the maximum readability, despite the wasted filter here. I think I changed this to sure is reachable. Reachable end is reachable, yeah. And this would suffice. So if we were to go super one-liner unreadable shenanigans, it'd look something like this. Then we'd even go further. We'd drop this to be a const too. I don't really personally like it. I like explicit over implicit, and as much as I love my functional, there's something nice about this that I'm going to keep. Let's go down to part 2. I'll turn those back on now that we're not consoling the world. Gross. Okay, we get to do this part at least. If end in distances, and then do the calculation of the rating. Now, I broke this into a function. I'm not opposed to putting it back into here, but I do like the fact that it's a function. What does this function need? It needs the previous. Okay, I'm willing to break this out. Previous, which is just a record of string arrays. Yeah, and then just pass that. I can pass that previous, because then I can just boop, 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 and it looks practically identical to the part 1, but our score calculation is a thing instead of a 1. Ooh, it's so tempting. Go the next level. And instead of having a function that we do this, we know if every end results in addition to the score. We functionalize this addition instead of this whole thing. I went far enough though. I'm not going to go that far. So we have that. We have calculation of rating. We need the distances. Yeah, I like that. How do I like this? I personally do. Would I like it more if it was true recursion? Let's try it. So what is this? Start and previous. I need all these. Hey, give back. Oh, I didn't mean to steal them. And then what? Path. Well, it's not path, it's current. We don't actually need the rest of them, which, good point. It's an optimization I can even make on the iterative one. Let's do that. And do for next. If we find it, return it. Otherwise, return the self. Why did I not just copy the things? Okay, now if I want to do it tail end, I'd have another call and I'd check if current equals end kernel one, right? And now I'm going to do all these other calls. So for next of this, these are all additional calls. So we have the sum. So let rating equals 0. Let's not delete that. Rating plus equal. Get the recursion call for in previous and then next. And then we have that working. So I think this will do the trick. I just need to kick it off with current, which is what I'm doing down here. So let's give this a shot. Or plus equal, not plus equal, minus. Into a new operator by accident. And start previous. And where do you actually start? Start at the end, I think. Boom, we got that. And yeah, I do think we are, if I recall right, we are getting some tail end recursion fanciness here. I mean, dang, this recursive one, they clean up nice when they clean up nice. Slash when I can think of them properly. Let me optimize this one also. Instead of start, let's drop it to this. So we can just say current equals paths pop. Then we just push next. And yeah, just to prove it still works. Kill it, swap it. This. Uh-oh. No. Go back. Go back. Oh, I boop, infinite loop. Come on. Did I save it? Okay, there we go. We saved it. So yeah, iteratively, I could do the early thing up here recursively. The recursive one looks really good. If I want to go further, I'll have the calculated rating, and then I'll have the recursive function inside to take advantage of a little bit of scope. So that's where I'm going. I'm going for the recursion. And at this point, let's take advantage of all the scope. Let's bring this up into here. Ooh, the naming of start and end do their swappy thing. You know what? Probably best that I do name it properly. So let's swap the names back while we're here. Drop all of these. Current is the only thing you got. You are starting at the end. You will give me numbers. Boom. Yeah, that is much better. And this can be thrown to a reduced map thing, which is what I will poke at next. Yeah, I'm just going to call you recurve. Maybe I'll poke at it. Let's see what it looks like. So that would be turn. Put your parentheses, because who knows? Actually, we do know. Let's see what's gonna happen. So I saw that yellow dot there. Okay, yep. So data structure generating all our things. We love it. Which makes this one lining a little easier. reduce a rating next, rating plus recur next, starting at 0. Ta. I don't know why it looks so weird. It's working. I think our types are a little faily. Yep, it does. I don't like it though. It's a little too fancy for my blood. Okay, I think that was as far as I'm going to refactor this. Save stage and smell time travel. Don't need to do that. Okay, final walkthrough. So, we made a little helper solve that takes in the data and a special way to measure the trailhead, whatever. Score, rating, choose your own thing there. So we all immediately call this with the data and the cool function. We'll get into the cool function later. We start off by parsing Lava Island. This has unchanged. We're generating a graph, but this time the graph, so I lied, it did change, is from destination to places you can go. So there's no more waiting. All our weights are 1 by default in the algorithm. And we keep track of our start and ending keys because we don't need to do any math on the objects aside from our neighbors. So in this function, we use keys, and instead of being an object, we just push the destinations of places you can get from here to all the places in this array. We have that, and then what we do is we add up all of our scores, and we calculate each of those individual scores by calling our super special function with the start, all of the possible ends, and the result of our Dijkstra call. That's the same for part 1 and part 2. And then in part 1, well, our calculation of the score is how many ends are reachable. So that's how many ends are reachable, which is represented in data form of how many ends we are able to get to or we have a distance to. So we add that by 1. I'll go through Dijkstra in a moment. Part 2, still using all that same stuff of places that we were able to reach. So the trailheads, the trail destinations we were able to reach. But instead of just saying each one we reach plus 1, each one we reach, instead, we need to calculate how many distinct paths you can get from the beginning to the end, or the end to the beginning. I decided to go backwards because that's the way my previous data structure worked. So we start at the end. In our base case, we try to get to the start. So we are here. If we haven't made it to the start, then we suck. But if we are just in the middle somewhere, then we look at everywhere we can go. So we continue the backtracking, and we add the result of calling recursion on that, which, again, it's recursive, it's not iterative, but if you can follow recursion, this is classic recursion. We got our base case, our tail end optimized. Then we have our calls for each of them, adding up the results of all of our subsequent calls and returning that result here. And then finally, there's the Dijkstra itself, which, again, not explaining core Dijkstra, but the modifications to it. I just cleaned it up, added a bunch of types, some initialization, got rid of that infinity because I didn't want to throw a bunch of junk in memory that I wasn't going to use. Converted that hash map that was being used as a set into an actual set, and got rid of the edging and the weights to just be consistent of 1 because we weren't actually using that. And yeah, I mean, the way this actually works is it goes through and it grabs every node we haven't visited, but is a neighbor to a node we can visit. So if we've never visited this node, but we visited a node that can visit this node, then we're going to pick that one. And then of those ones, we're going to choose the one with the least distance. So the one that is closest to us. If we can't find anything, we give up. Once we do find something, we say we have visited it. We go through all the places that we can go from our current node, and we say, hey, like keep track of your previous of like we were able to get from here to here, and then say, hey, we are going to visit you at one point in the future. Which, as I'm looking at this, we could completely eliminate and just rely on one data structure. But I don't want to do that. We're good enough right now. Well, that was the last of it, actually, yeah. So, that was Advent of Code, Day 10. A pretty fun one. Don't see myself visualizing or gamifying it, to be honest, but it was a good one. And as always, it is a pleasure. Till next time.